In this video, I'll be going through a worked example related to the learning objective, solve problems involving two-slit and multiple-slit interference, specifically multiple-slit interference or diffraction gratings. This question comes from ACE Physics Syllabus Code 9702, Paper 11, from May-June 2011, question number 27, and it reads, a diffraction grating with 500 lines per millimeter is used to observe diffraction of monochromatic light of wavelength 600 nanometers. The light is passed through a narrow slit, and the grating is placed so that its lines are parallel to the slit. Light passes through the slit and then the grating. An observer views the slit through the grating at different angles, moving his head from X parallel to the grating through Y opposite the slit to Z parallel to the grating on the opposite side. How many images of the slit does he see? Hopefully, as I was reading through that, you were sort of visualizing this creepy floating eyeball on the page kind of moving like this, right, parallel to the grating. And so really the question, it seems kind of like a bizarre question, especially if you're, just being introduced to the physics of this, like, how many images of the slit does he see? So sort of the observer would be kind of moving their view kind of like this. Really what we want to try to do is anchor our thoughts on equations in physics, right? And there's some clues here sort of with the values. But as soon as you see diffraction grating, the equation that should come to mind is d sine theta equals n lambda. And as soon as you know that that's the equation that's helpful in solving this, then you can kind of think about, well, what am I solving for here? And again, I've mentioned in previous videos, don't just over-rely on your knowledge of the equations or your ability to memorize equations and say, oh, as long as I know d sine theta equals n lambda, any diffraction grating question I get, I'll be able to solve without really understanding the concepts. This is a good worked example to really focus on why it's important to have a conceptual understanding along with sort of, the mathematical knowledge as well to answer it correctly. So let's think about it. The first thing is we're told the diffraction grating has 500 lines per millimeter. Remember that the distance d is the distance between each line. And so let's just kind of write out what we've got. We've got usually what we'll call this, when we know lines per millimeter, we'll call that capital N. Okay, so we'll say there's 500 lines per 1 millimeter. But I'd prefer to know the distance between each line. And so I want to kind of think about this as the distance is going to be 1 millimeter per 500 lines, which is the same thing as 1 times 10 to the negative 3 meters per 500 lines. And so if I want to know the distance in meters between each line, then I need to take that ratio. So I have 1 times 10 to the negative 3 divided by 500, and that's the value d that I'll need for my equation. 2 by 10 to the negative 6, right? So that's one of the first things that we have to do, is really deduce the value d that we can substitute into this equation. The next thing that we need to think about in the equation is this term sine theta. This equation is telling us how much light of a given wavelength is going to diffract, to spread the angle there. And it's measured from the central order. And so this point y here, where we sort of see the creepy eyeball floating opposite from, that would be like where the zero order would be. And what we're solving is the angle sort of relative to that. And so we have to keep in mind that 90 degrees is the maximum angle that we have here. And so sine 90 is a maximum value. Sine of 90 degrees is 1. That's the way that we need to think about this term, is that it just sort of goes away from the equation, just sort of vaporizes. We're sort of saying how many images does he see, and so that's a maximum. And so we need to plug in sort of the maximum value here. Sine 90 degrees or just 1 for that. So that's kind of nice. We don't need to really worry about that term. remember, n is kind of the thing that we're solving for, but if you paid close attention there, then n is telling us the order number relative to the 0 order, right? And so let's say there was our first order maximum, at some angle theta right here, okay? And maybe there's the second order maximum and so on. We're trying to figure out how many, we're solving here how many are on one side of the 0 order. So anytime you get a question like this, and there are different sort of variations of this type of question, it's actually a pretty typical question that we see from year to year, where you're solving some sort of variation on this theme here. It's very important that when you solve for n, you're solving for the order number on one side of the 0 order. So you always have to double it, right, to get all of the orders like on this side of it from like y to z. And you also have to include the 0 order itself, right? That's also an image that this observer is going to see, the 0 order itself, directly across from point Y. So that's important enough that I might just sort of write it out here, just so we can always keep that in mind when we have this type of a question. The wavelength we were given, right, 600 nanometers, we just have to take care of the nano. Remember, we've got our distance d here in meters. And so let's go ahead and solve this now for n, by dividing each side by lambda and substituting in some values. So here we can see d is 2 by 10 to the negative 6 meters. Sine theta is just 1, so I don't need to write it. And nano is 10 to the negative 9. So we've got 2 by 10 to the negative 6 divided by 600 by 10 to the negative 9. And that gives us 3.3 repeating. We can only see whole order numbers. And so this 1/3, we wouldn't even, and it's not like we're even rounding down. If it's not a whole number, we always have to round down to sort of the nearest whole number. We can't see a fraction of an order number. So this observer would see, the first, second, and third order maxima above the 0 order. Some students that are quick to substitute in values, even that have made short work of like, we're really given this an n, so we've got to take its inverse to know the value d, the distance between the lines in the diffraction grating, could plug all this in and see the answer in the calculator and incorrectly choose choice A. Some students may remember to add in the 0 order, and they would incorrectly choose choice 4, or the answer 4 here, choice B. Some students may be mindful that they've solved it this way, and they've doubled it. They've thought, oh, but we've got all of the order on the other side of the 0 order, right? And so they double the 3 orders they'd see above point Y here, from Y to X, and they would get 6, and they would incorrectly choose choice C as the answer. Only the student that remembers to double order n and then add the 0 order, right? Remember, there's always a 0 order, that white spot, okay, when we're looking at the diffraction of white light. See the link to the video there. So any type of question like this, where we're solving for like the maximum order number or how many images will be seen, we got to keep in mind that sine theta is 1. We're using the equation d sine theta equals n lambda. Sometimes we might be given information in order to calculate the distance d between each line and diffraction grating like we were here. Usually we'll call that like n. There are 500 lines per millimeter. And then as long as we take care of the units, we should be able to plug in everything and solve this. So the correct answer here is choice D.